So let's take a look at two elements here. We've got two volume elements. This is going to have a volume of a unitless side on each face. So we end up with an initial volume equal to 1. Right? Stresses are applied. So there's a sigma y, there's a sigma x, there's a sigma z. These stresses are applied, so we would know then that the new volume would be the multiplication of the three sides. And the three sides would be expressed as 1 plus the strain in the x direction, same with the y, and same with the z. So if we go ahead and multiply that out, we end up with 1 plus epsilon xx plus epsilon yy plus epsilon zz. And then we have order epsilon squared, and we know that epsilon, these strains, have to be extremely small, so that goes to 0. So we find out that the change in volume, right, which would be the new volume, which is sitting right here, subtracted from the initial volume, so the 1's going to cancel, and we end up with the change in volume is equal to the sum of the normal strains. So we're going to take that and now just plug in the expressions that we've derived for epsilon xx, yy, and zz. So the change in volume, the expression for epsilon xx, right? This is off your equation sheet or about the original derivation. So this would be epsilon xx. And do that 2 more times. There would be epsilon yy and epsilon zz. And all I'm going to do is add them together. And when I add them together, I end up with the summation of the stresses. And I end up with this quantity out here. So it might take you a minute. E is in all of the terms, and we'd have a 1 minus 2 times Poisson's ratio. So now we've expressed the change in volume in terms of stresses. So pretend like we take this cube down to the bottom of a pool or deep into the ocean. So we have hydrostatic pressure on all faces. So we would have a triaxial stress state. And the applied stress would be equal to the negative of some pressure value, right, where P has to be greater than 0. So if we go ahead and plug that in, right, we just end up with minus 3P, which would be the sum of all the stresses multiplied by the quantity 1 minus 2 times Poisson's over E. Now, if we take that thing down into the bottom of a pool or deep into the ocean, the volumetric change would be less than 0. It would shrink. It would contract in all directions. So we'd have a volumetric change of less than 0. So we're just going to apply that to the equation above. So the change in volume, sitting right here, has to be less than 0. So I write it there. I can go ahead and get rid of some constants. P and E, multiply by those go away. I can get rid of the 3 as well. So I'll give you the next line. And distribute the negative across. And we're almost there to Poisson's ratio has to be less than 1. So that tells us that Poisson's ratio, its maximum value, can be 0.5. And the reason why it has to be greater than 0 is if it were not, that would mean that when we pulled in tension, that we would actually get something that expands. Which when we pull, there's no natural material that would do that. So we end up with the bounds on Poisson's ratio has to be between 0 and 0.5. It's going to be a positive number.